Sorry.
Yes, I was saying this is welcome to this presentation. This is our last presentation for the day. So it's our pleasure and honor to have with us today Professor Sophie Tarbouriech. So let me just say a few things to introduce our speaker. Professor Tarbouriech is a director of research with CNRS in Toulouse in France. She has made many important contributions in various areas of control, like nonlinear control, hybrid dynamical systems, event-based control, and has also worked in a number of applications. She has been in the editorial board of various control journals, and she has been an active contributor to many activities of IEEE and IPAC. She's, for example, a current member of the IEEE Control System Society Board of Governors. So today, she's going to be talking about dynamical systems with isolated nonlinearities.
Thanks, Eunice, for this kind introduction. So I would like to thank the organizer for the invitation to give a talk today. I am very happy because it's my first conference in person since the pandemic. I suppose as for many people in this room. Today, I would like to share with you some ingredients regarding dynamical systems involving isolated nonlinearities. I have to emphasize that all the results I will discuss with you today are due to collaboration with national colleagues or international ones in the broad regions. So, as mentioned by Eunice, the title of the talk is a journey on dynamical system involving isolated nonlinearity. Oh, this one. No, this one. No, this one. Okay. Oh, sorry. Sorry. So the outline of the presentation will be the following. First, I will give some general motivation for the studies. I will present some insights regarding isolated nonlinearity. And I will propose a focus on saturated system, that is a system with saturation in input. I will provide some generalization of these first items, and I will give some new insights regarding the new forms for Lyapunov functions, and I will finish with some wrap-up of the presentation. So, of course, all the dynamic systems are subject to constraints due to physical, safety, or technological reason. For example, we can have a look on the pump of the valves, the push needle, the converters, and so on. And we need the motivation to study the system with constraints is to be able to take into account these constraints in order to be able to provide some desirable properties for the system, like, of course, stability, performance, or convergence. Okay, so in general, the constraints affect the actuators or the sensor of the system. We can find several examples in the literature in the world, the aircraft, civil or combined aircraft, the fleet of satellites. We can also work on the cross-directional control for synchrotron, or we can also work in the context of medical area, for example, in the control of anesthesia. Okay, so and in order to take into account all these constraints, in order to provide good properties for the system, we need to develop some adequate tools in order to do this. No? Okay, I will start by presenting different types of nonlinearities. The first one are related to the practical limitation of actuators and sensor, for example, saturation, of course, but also dead zone, hysteresis, or discontinuity. For example, when we have some ingredients like this in the loop, we have some discontinuities and dead zone in the context. And I provide also several references of some authors studying this kind of nonlinearities. We have, sorry. We have also the constraints related to the communication channels or the information capacity of the system. And in this case, we need to take into account some quantizer, coding, decoding. And for example, in the picture, there is two kinds of quantizer, the uniform one and the logarithmic one. And I provide also some names of researchers working on this kind of nonlinearities. We have also the constraints due to the problem we are studying. For example, when we work on the control of anesthesia, here it's a picture of the BIS problem in anesthesia. We have to take into account, for example, the positivity of all the variables. When we work with, for example, neural networks, we need to take into account some activation function, like the ReLU function or the RAM function. When we work, for example, when the problem to prove the convergence of some optimization algorithm, we need to take into account in the dynamical system, representing in a certain sense the problem of optimization, we take into account the gradient of the function we want to optimize. Okay, I provide here also some references of researchers working on this kind of nonlinearity. Okay, so what are the main objectives when we want to take into account this kind of constraints? We want to be able to develop some certificate in order to guarantee the properties for the system, as I mentioned before: stability, performance, robustness, safety, tolerance, the algorithmic convergence, for example. And in general, these kind of properties are difficult or even impossible to check analytically. So the solution we propose is to develop some abstraction sufficiently representative in order, if we have this kind of condition, we can provide the certificate of the property. Okay, I can just give to start a very simple example. There is a baby, and the baby tries to control its position from the ground to the stand up, of course, and we can study this problem. Like the baby can be modeled by an inverting pendulum. We can imagine, from a control point of view, of course, that the diaper is a sort of uncertainty. And we can also consider that the constraints in this control problem is the muscle strength of the baby. Okay. No. Okay. One of the nonlinearity which is very interesting, at least from my point of view, is the saturation. Why? The class of saturation, the saturation is in a class of nonlinearities, which is simple, apparently, but in fact, relatively difficult to manage when we study the system. And in plus, we can imagine to use the saturation in order to approximate other kind of the nonlinearities. I provide two examples here. The first one is, if you remember the plenary this morning, Andrea spoken on the aircraft, and in aircraft we have several limitations in magnitude, rate, acceleration, and so on. And in general, these nonlinearities are directly magnitude, rate, saturation. And one of the famous example, and the fact to take into account the pilot induced oscillation in the aircraft, and we need to provide some techniques in order to prevent this problem in the aircraft. Or we can also study a fleet of satellites and provide some guarantee of stability. Okay. Another interesting way I mentioned is we can use saturation in order to approximate other nonlinearities. It's typically the case when we study, for example, the robust landing or on-ground control for civil aircraft, and we can approximate some ground force between two saturation like this in green, for example. And due to the fact that we need to estimate what is the level of the saturation here, we can, thanks to this estimation, have an information on the state of the road, icy, wet, or dry. Okay, so we can, thanks to some techniques developed for the saturation, use this in order to deal with other different problems. Okay, so the main idea is very simple. We want to be able to embed the nonlinearity and provide some abstraction in order to deal with this kind of nonlinearity. So we consider the following nonlinear system, very classically, affine in the input, and we support that we have a nonlinearity psi of u in the input, and we want to provide some sector conditions for the difference between the nonlinearity and its argument. That is, I denoted this like phi of u being the difference psi minus u. And I want to be able to provide some condition described in yellow here, where we retrieve the nonlinearity phi here, multiplying a certain nonlinear function. We will see after what happens with this function. And this quantity has to be positive or null in a certain set. So we need, in fact, to define h and omega in order to embed our nonlinearity. We have here a classical picture. We can pass from a saturation to a dead zone here and study the dead zone instead to study the saturation. We can use this kind of tools in order to manage different problems like the stability analysis, the optimization. We can the optimization of the region of stability. We will see after what happens with this kind of region. We can also use this in order to be able to design some anti-wind-up schemes. We can also use this when we have some delay in the loop or some sampling, or when we want to develop some event trigger control, for example. Of course, in the literature, there exist several different methods. For example, we can use differential inclusion in order to embed the nonlinearity. We can also use some piecewise affine description or quadratic constraints, and I denote some famous author in this context. But sometimes, in particular, for example, when we want to design some anti-wind-up scheme or when we want to design the controller, this kind of method can reveal to be more complex or more conservative to use. So it is a reason for which in this talk, I choose to present this kind of tool. And what is the motivation to use the difference between the nonlinearity and the argument of the nonlinearity? It's clear in this slide. So we rewrite the system like this, where we use phi now here. And why we do this? Because we have the assumption that the linear-like system, that is this system here, will be stable. Okay, so now I am studying a system with a stable part and this part. It is important because if I come back to this system, I have no assumption on f of x. Okay. Oops, no. No. Okay. So from this change of loop, which can be seen as expansion of change of loop in the context of absolute stability, we want characterize a certain Lyapunov function V and use the condition we obtain for the nonlinearity like this. So we will search for Lyapunov function satisfying the classical condition on Lyapunov function, and we will use the knowledge we have on the nonlinearity in the context of the study of V dot, that is the time derivative of the Lyapunov function, through this equation. We will see how we can do this. Okay, so of course, I will do a focus on saturation, and we will come back at the end of the presentation on other nonlinearity and how we can revisit the study of this nonlinearity. We can use exactly the same idea, of course, differently depending on the nonlinearities, in order to revisit other types of nonlinearities, like, for example, mechanical play, like backlash or hysteresis, depicted in this picture, for example. And I put also some researcher working on these kinds of nonlinearity. Okay, so I want to do a focus on a linear system with saturating input in order to study stability analysis and control design. And I would like just to mention that the linear system with saturating inputs sit at the boundary between linear and nonlinear worlds, because even if the open loop system is stable, we cannot conclude directly that the closed loop system will be globally asymptotically stable. Okay, and we need to take into account the nonlinear effect of the saturation in order to study the system. And indeed, if we consider the stability, we study the stability of the system, we can prove the stability to be local or global. Of course, if we forget the saturation, because we are studying a linear system in this context, we will have the global stability. Okay, that is, we can stabilize all initial conditions in the state space. It will be not the case for the saturation. Okay, so we consider a very simple system, linear system described in the 5 equation, where we consider that the input is a state feedback control. And we need to observe that the saturation is indeed an abrupt nonlinearity. Why? If I evolve around the origin, I will consider small signal, and in this context, I will have sat of u equal to sat of u, and the saturation has no effect on the system trajectories. Now, if I suppose that I am far from the origin, I will have to deal with large signal, and in this context, sat of u, I have to use the fact that sat of u is uniformly bounded, and therefore there is a severe effect on the system. I can just show this on a very simple example, the pointer balancing. That is to try to stabilize this kind of system. It's not my case. So I take a first initial condition, not so far from the origin. What happens? During a certain time, the input remains saturated to the minimal value -5, and after a certain time, converge to 0. It's the same for the state x1 and x2. I choose another initial condition here, not so far from the first one. What happens? The input remains equal to the upper bound on the saturation, that is -5, and the first state converges to 0, but not the second one. It converges to -5. So we have the fact that we have another equilibrium point, that is, we have here an equilibrium point at 0, -5. And what happens if I continue to change my initial condition like this? I will obtain that the saturation, the input remains in saturation at the value -5, and my state is diverging. So it's clear we cannot obtain, for this example at least, the global stability of the regime. So we have just depicted the fact that we have some initial condition allowing to stabilize the system, and other one for which it is impossible to stabilize the system, and we obtain diverging trajectories. So we need to define the region of attraction of the origin, denoted RA, And this region is the set of all the initial condition x0 leading to solution converging asymptotically to the origin. Okay, so we can say that RA0 is the exact stability region of the saturated system. Of course, sometimes this region is equal to all the state space. And in this case, we say that we have the global stability of the system. And in general, this region is different from all the state space. It's just a sublevel of this a subset of this space. And in this case, we say that we have the regional or the local stability. And we have here a picture in the context of bilinear systems. In blue, it's a true region RA, obtained not analytically, but by simulation. And we see that it is interesting because we obtain just by simulation. And when we have a more complex system, it can be very difficult. So it is important to be able to provide some approximation of this system. And for example, by using quadratic Lyapunov function, we obtain this approximation of the true region of attraction. So it is the objective we want to deal with now for the system. So we come back to our previous system. So we consider classically this system. It is interesting because we have the change of loop like this, and we retrieve that this matrix is of this. Okay, and we pass from this to this. So we start with the global exponential stability. So we use the classical sector condition. So there is a T-pose, there is a transpose here, of course. It's good. Here, there is a phi transpose multiplying T, multiplying this expression, where T is a positive definite diagonal matrix. And this condition is negative for any X belonging to Rn. So we say that we have a global sector condition. So we have a linear system. We search for a quadratic Lyapunov function described classically like X transpose Px, where P is a symmetric positive definite matrix. And we want to combine, in order to study the sign of V dot, we want to use the previous condition. So we plug in the expression of V dot here with the expression of the sector condition here, and forget that here there is a transpose. So we can do this because this quantity is positive, because we have add minus. So we can say that V dot is less than this expression. And in order to prove that V dot is negative, it suffices to prove that this expression is negative. We can report this result on the following theorem. So given K, because we are just studying the stability analysis, we have to find W, symmetric positive definite matrix, S, a diagonal matrix, positive matrix, such that Ng is definite negative. Then if I am able to find both matrices W and S, then I can prove, I can ensure that for any initial condition in Rn, the closed loop system previously defined is globally exponentially stable. And I retrieve the previous sector condition by considering T as the inverse of S, and P, the quadratic Lyapunov function, is the inverse of W. We can remark that the condition 7 is linear in the decision variable W and S. We can also imagine to search for design K, and in this case, we can replace classically K, the product K W, by a new decision variable way, and we keep the linearity in the decision variable W S way. Okay, but what happens with this condition is very nice, very simple. What happens with the feasibility of this condition? I can multiply at left by the matrix, so identity B0 identity, and by the transpose of this matrix, the condition Mg. What happens? I retrieve that the fact that Ng has to be positive, then I have this quantity negative. And what happens if I have a look on the condition? What happens? I need to have this quantity negative. So what is the meaning of this? The meaning is A has to be this. That is, the open loop system has to be globally exponentially stable. So it's a very dramatic limitation in order to study this kind of system. And we recover the well-known limitation in the literature in these famous papers. Okay, so we can go further and prove that we can obtain the global asymptotic stability by relaxing a bit exponential by asymptotic, if and only if the matrix A is not exponentially unstable. So we understand that we have non-global condition, and we are ready to study regional sector condition. And we can do this now, normally. So always the transpose is missing here. So we write a condition on file like this, and the very nice novelty is the fact to use this quantity g of x in green, and we can prove that this quantity is negative for g of x in the dead zone, okay, where t is also a positive diagonal matrix. So we will say that this condition is a regional sector condition because it's not for any x, it's for the x only in this region, okay? So we can recover the previous classical global condition. Why? We put g equal to 0 and we recover the previous condition, okay? So we use exactly the same reasoning by combining v dot with the sector condition in order to check that this condition is negative, and we can report this on the following results. Okay, so if we are able to find W, symmetric definite positive, S, diagonal positive, Z, and a scalar lambda positive, such that both conditions are satisfied, then I can prove that my closed loop system is locally exponentially stable for any initial condition in this level set. And in plus, this level set is always a subset of the region of attraction of the origin. Okay, so I can recover the Lyapunov function like this, as previously, T as previously, and I retrieve G like this. Okay, and I can have exactly the same remark on the linearity in way S, Z, or also in W, S, way, and Z as previously. What happens with the feasibility of these conditions? It's better than previously. And the answer is yes, because if I look at the condition, I can, due to the expression, I can choose a particular solution Z, for example, written like this here. What happens? MR is now this condition, so we cancel the off diagonal terms, and we need to satisfy that this quantity is negative. It's always true because S is positive, and A plus BK is a Vitz matrix. So there always exists a W symmetric positive definite satisfying the negativity of this part. Okay, so I can keep this solution W and S, and I look at the second condition here, and I can write by using the Schur complement the equivalence of this condition positive is equivalent to satisfy this condition, and there always exists a lambda positive satisfying this condition. So these conditions are always feasible, okay? And I can just comment this. I forgotten to do this. The first one corresponds to the stability condition. And remember that the sector condition is only valid in the dead zone, that is phi of Jx has to be equal to 0. And this quantity, this condition is to check this condition of validity. So we can always, for any system, study the regional stability of the system. Maybe I can continue, maybe not. Okay, we have seen the state feedback. We can go further and study the dynamic output feedback, and we have the classical plant described by x dot p, y p, and we consider a dynamical controller xc, yc, described like this. Okay, and we have this picture. Okay, so it is well known that if we have not this red box, that the, and we also, I forget to mention this, we want to design a dynamic output controller of the same order of the plant. Okay, so NC is equal to NP. It's well known in the literature that the condition for designing AC/DC, CC/DC without the saturation are linear in the decision variable. For example, we can use the condition issue from the Scherer and co-authors proposition. And what happens now if I add the red box? The condition becomes nonlinear. I cannot obtain convex condition if I want to design AC, BC, CC, and DC in presence of saturation. But I can use some trick. I can use some knowledge on the saturation by picking the input and output of this term and adding this term through the state EC, that is correspond to theta in this dynamic output feedback. And now I am able to prove that the global and regional condition for designing AC, BC, CC, DC, and EC are linear in the decision variables. And why we can prove this, just a small insight. If we consider P defined like this, it's completely classical for this kind of design. If we have not the anti-wind-up term, we have not the orange term here, and we have a product between X and S, we cannot design X and S, it's nonlinear. But if we add this condition, this term in plus, that thanks to theta, we can denote like this expression like R, and we can use the classical trick in order to recover X, S, EC, U, and so on. Okay, so we can guarantee the convex conditions thanks to the anti-wind-up term theta. I mentioned before that we are interested by optimizing the size of the approximation we provide for the region of attraction. It is important to note that the set we obtain described like this is a linear approximation of the region of attraction, and we can maximize the size of the set. We can use several criteria. I put just two of them. For example, we can minimize the thrust of the inverse of W, and we add some condition in plus, or we can also maximize in certain direction the set, and we have to consider several additional constraints. And we can depict this on a very simple example. We are in blue, the maximization of the thrust, and in black, the maximization in some direction, and we maximize the direction 0, 1 in this context. It is very important in the zoom to see that the system is very close to the parasitic equilibrium point in general. So it is interesting because at least in this direction, we obtain the better approximation we can. Of course, we can also study different problems, like the fact to optimize the size of the actuator. And for example, we can search for some norm of U0 being the level of saturation, in order to minimize this norm for some given set of initial conditions, in order, for example, to reduce the energy of the consumed by the actuators and so on. Okay, quick summary of this part. We have provided some ingredients in order to propose some abstraction to deal with the saturation based on a generalized sector condition. We have considered linear state feedback, linear dynamic output feedback, and we use mainly quadratic Lyapunov function. Okay, and we propose a linear approximation of the region of attraction. Of course, we can expand all this approach when we deal with more complex systems. For example, for system with nested saturation, it is typically the case when we have magnitude and rate saturation. It's the case, for example, in the context of civil aircraft, combat aircraft, or launcher, for example. Okay. Okay, we can also use this condition in order to study different nonlinearities like quantization, friction, and backlash, and we will do a focus on this later. And in this context, the objective is to characterize the attractor around the origin for this system. And in this context, we will provide an outer approximation of the attractor, because if we have in mind the system with saturation, the attractor is a point, is the origin. And in this context, we have a parasitic equilibrium point limit cycle, and we want to be able to characterize the region in which these points or limit cycle are. Typically, we have a picture with the backlash or with a quantizer, or with backlash with, for example, a limit cycle extremely close to the boundary of the system, or parasitic equilibrium point for the quantizer. We will do a focus on this later. So we can expand the control law we can study. We have studied until now linear control law. We can expand to nonlinear control law, for example, U of X, where we define the control from this. I use exactly the same notation as previously, but in this context, the control gain K will be nonlinear in X, will depend on a certain scalar sigma depending on X. Okay, so we can say that the gain is scheduled in the scalar by the scalar sigma. So we consider the same condition, but now we expand the condition. That is, we consider that the matrix T can depend on the sigma and also G of X. Okay, and we have always this condition because we are interested in this context in the local stability. And T is always a diagonal positive matrix, and we support that the scalar sigma is in an interval between the lower and upper bound sigma bar, like this, and we consider a more complex Lyapunov function using also the function sigma of X in the Lyapunov function. And we will see that this equation, and we will see after that this matrix and this scalar define the approximation of the basin of attraction from this. And we will use the implicit equation here to prove that we have a unique solution. And we can report this in the following results. So support that we fixed the upper and lower bound for sigma. And if we are able to find W, S, Y, and Z, and alpha satisfying this condition, so it is very nice to see that this condition is globally the same as previously. It's an inclusion condition. We normalize the saturation in order to remove U0, but because the level is 1 now. And here we will try the condition of stability. Here we have a condition for the conditioning problem, and here we have a condition depending on sigma, because we have sigma in the Lyapunov function. Okay, and here we use the Schottland notation in order to save place. Okay, so if we do this, we can prove that we have the well-posedness of the loop, because we can prove that the implicit equation has a unique solution, and it is important to use the sigma in the control law. And we can prove also that this function is Lipschitz for all the X belonging to the inner approximation of the region of attraction. And we can compute the static nonlinear state feedback like this by keeping the value sigma star and so on. And in the set here, we can guarantee the exponential stability of the system. Okay. We can just illustrate this, and we can just note that we choose to consider dependence on W, T, S, sorry, and G, and so on, polynomial dependence of this matrix in sigma. And in order to solve the problem, we use SOS relaxations in order to exhibit the solution for the controller, the Lyapunov function, and so on. So we take a very simple example like this. We choose this value for the lower bound and upper bound for sigma, and we choose polynomials of order 4 for W and so on. And we obtain the following picture by choosing this initial condition. Okay, we have the convergence of the state, and we have a saturation of the U during a certain time, and after the convergence to 0. We also provide some noise. We also consider some noise in the state in order to prove that we have some robustness. It's a reason for which we have some shattering here. And we prove that we have a certain convergence with a certain exponential bound. And we can, if we compare with other approach, in particular, just static state feedback, that we can improve the rate of conversion by using this kind of controller, in particular, in the context of global case. So we can continue to generalize, and we can consider a system, nonlinear system described by polynomials, described like in a yellow equation. So now you understand the idea. We expand the condition. That is, we consider that T of X will be also a polynomial function, and G of X also. Okay, and we use the same condition and the same idea in order to build the linear approximation. So in this context, we need, if we want to design the controller, we consider a quadratic Lyapunov function. And by using some representation of all the new augmented system using different moments of the polynomial state x, x1, x squared, and so on, but with a tricky definition, we can recover, thanks to the fact that we use the quadratic Lyapunov function, classical change of variable in order to design directly the gain, the state feedback gain, depending of x. Okay, and when we want to analyze the stability of the system, we can use polynomial Lyapunov function. And as previously, in order to check the non-negativity of horrible polynomial conditions, we can use SOS relaxed SOS constraints. And we have just a small example. We pick this example from the literature. We have the level of saturation is equal to 3, and we consider two control law, polynomial of degree 1 or degree 3. Here it's degree 1, degree 3 here, and we consider Lyapunov function of degree 4. Okay, so what happens in magenta? We have the region of validity of the sector condition. Remember, it's phi of G of X equal to 0. In blue, we have the true region of attraction obtained by simulation, and in green, here we obtain the region of the approximation we obtain with our condition, and here we obtain a better approximation, but ultimately to augment the order of the polynomial of the control. So we have to do a trade-off between the degree of the Lyapunov function and the degree of the controller we can admit in order to approximate the system. Recently, there is some extension of this approach by relaxing the fact that we need to choose quadratic Lyapunov function in order to design the control, because we can use different Lyapunov function, and we will see which kind of Lyapunov function we can use. That is, we can relax the positivity of the Lyapunov function, and we can use sign indefinite quadratic forms as described in orange. And in this matrix here, this matrix is sign indefinite matrix. Okay, so if, of course, we impose that P11, for the moment, we impose that P11 is positive definite, but not this matrix. It's the main difference with the previous approach. Of course, this kind of Lyapunov function has been studied in the literature, but generally, the researcher imposed that this condition, this matrix has to be positive, even if some recent works start to exploit the flexibility of matrices which are not sign definite. Okay. So it is interesting to use this kind of Lyapunov function because we can recover the classical Laurier function. I denote two examples because the first one is used in the paper of Day and all in 2009, and this is in the book of Khalil. Okay, and the difference, the main difference is just the definition of the integral terms here and here. Okay, so in order to recover this, we can use the previous definition of V. We can exploit the identity that is multiplying this integral is equal to 5/2. And of course, due to the fact that P is not positive definite, we need to impose some positive definiteness and radial unboundedness by using the knowledge we have on the condition phi, because remember, we have a function defined from X and from the dead zone. Okay, and it is also interesting because from the previous form I presented, we can do also a link with the quadratic separation. For example, we can see some papers from Possel and his co-workers. But in this context, the Lyapunov function is obtained a posteriori, and a posteriori, the Lyapunov function has the previous form as I presented. So it will be interesting to do a more deep link with this approach. So we can illustrate this. We can, of course, study the global or the regional stability. We consider a classical system like this, but we complexify a bit the controller by adding also the dead zone in the control. So we need to study the well-posedness of the loop, but we can do this. Okay. And we can illustrate on a very simple example described by this data that we can reduce the conservatism obtained by using quadratic Lyapunov function, because it is a well-known example in the literature, and we cannot globally stabilize this example if we use the quadratic Lyapunov function. We cannot prove that the system is globally stabilizable, even if we know that the system is globally stabilizable. And by considering this data, and we test our condition, and we obtain, effectively, we prove that the system is globally asymptotically stable. We have in red the trajectory, the closed loop trajectories, and in black, it's the sublevel of the Lyapunov function. And it is interesting because if we have a look on the shape of the trajectories, we can understand why it is impossible to prove the stability with quadratic Lyapunov function, because we cannot embed the trajectories in the quadratic Lyapunov function like an ellipse. Okay. So we can also deal with the local stability. Okay. And in this context, is also the same, and sorry for this, is also the same for the global stability. We use the sector condition for phi of u, the time derivative of phi, and so on, and we provide that the conditions are valid in this set. We obtain regional stability conditions which are quasi-LMIs in the sense that we have just for the inclusion positive parameter multiplying a matrix. So we need to do a grid to search this parameter in place of the matrix. It is interesting to note that we have defined V, but the Lyapunov function is W of X, defined like this. And the sublevel allowing to obtain an approximation of the region of attraction is this set S of W1. Okay. And it is depicted on this function, this here we have in blue red the set of validity of the sector condition. In magenta, it's a quadratic sublevel if we use just a quadratic Lyapunov function using several optimization criteria. And in black, it is the region of the approximation we obtain. And it is very interesting because we can note that we can obtain, and it's the case in this example, some non-convex set because we can have some small piece here. Okay. And we do this for different optimization criteria. We obtain two examples here. Okay. So some concluding remarks regarding this talk before providing some focus on other nonlinearities. We have proposed some LMI conditions for global and regional stabilization for linear systems subject to impute saturation. We can deal with different kinds of systems, linear, polynomials, but also rational, I did not present anything regarding this, but we also study this kind of system. We can use different classes of Lyapunov function, quadratic, polynomials, but now sign and definite quadratic forms. Of course, many other important techniques were not mentioned in this talk. Anti-wind-up techniques, the allocation function. You can remember the talk of Andrea this morning regarding this. The problem of contraction, if we want to study the problem of consensus or synchronization, for example, for a multi-agent system, and so on. And I would like also to say that we have studied the system subject to saturation or dead zone, but it can be interesting to add saturation and dead zone in order to improve the behavior of the system. For example, we can consider that a linear system describing the control for anesthesia during a surgery. We can forget in the first time the, of course, saturation we have, the true saturation we have, and we can design some observer or dynamic output feedback, to which we will add a new term built from a saturation or dead zone function with a variable level. And by adding this, we can deal with the outliers affecting the output, the measured output, or high frequency measurement noise. And we have just a small picture. We have the behavior of the control in the context of anesthesia with noise. It's very bad. Okay, it's not admissible. And we had the dead zone, and we obtain a drastic reduction of the influence of the noise for the answer of the same input. Okay, so it can be interesting. Now, to finish, we can come back to other nonlinearities. For example, in the context of backlash, we have the system described in yellow. And in this context, the nonlinearity psi of u is a time invariant nonlinearity, like the saturation with slope restriction, but differently from the saturation, is a memory-based operator. Okay, so we can develop with the same spirit some sector-like condition involving phi and phi dot, phi being always the difference between psi and the argument of psi, and we can provide some outer approximation of the attractor around the origin of the system. It's depicted here, and the nonlinearity, the evolution of the nonlinearity is depicted at right. But we can also use another things issue from the saturation framework. We can use some non-standard anti-wind-up in order to modify the controller, in order, for example, to reduce the oscillation of the system in presence of the backlash. And for example, we test this on a system representing a certain civil aircraft. We have in blue the result of the behavior of the output in presence of backlash. And now we plug in an anti-wind-up, a non-standard anti-wind-up using the difference between phi and LU, and we obtain the curve in red. So we reduce drastically the influence of the backlash on this variable. We can also consider similarly the problem of quantizer. Okay, we have the same kind of system. We have in this context, we use the uniform quantizer, described like this, where delta is the error. And we need to use the Krasovsky solutions to embed the system through differential inclusion to recover Krasovsky solutions, because the quantizer imposes to consider discontinuity in the system. But we can also use the same spirit in order to be able to provide some outer approximation of the attractor for the system. And we can also use non-standard anti-wind-up loop in order also to reduce the bad effect of the quantizer on the output. And we use this, for example, here. We consider the quantizer on the input, and on the input, we just plug in the anti-wind-up in between this time, and not here and not here. And we see that we reduce really the bad behavior of the output. So it is very interesting to continue to work with this. We can also study a system with a friction. We can represent the system with a hybrid framework, but we decide to follow another route. We can study embed the system in sector-like condition, but by considering two zones, the first one here and the second one here. And in this context, we study the outer approximation of the attractor in this context by considering this differential inclusion for the system. We can define the outer approximation of the attractor. And when we have, we have this nonlinearity here. Here we consider all the nonlinearity and we embed here in this gray zone. And here we consider this part of the nonlinearity, and we consider to embed the nonlinearity, this part of the nonlinearity in the sector in order to be able to provide a linear approximation of the region of attraction. And in order to be able to prove that the origin is globally asymptotically, we are able to prove that if the speed of the system mechanical part is in these intervals, we can prove that we have a global asymptotic stability of the origin if we are able that the attractor, outer approximation of the attractor, denoted like this, is included in the inner approximation of the basin of attraction. And we have the case here. We obtain the inner approximation of the region of attraction in the red, the outer approximation of the attractor, it is included. So we can prove that for any initial condition, we have the here we have the stability of the origin. Okay, and to conclude, to finish, of course, there exist several open directions, in particular to be able to deal with asymmetry. And we think that the use of the sign and definite quadratic forms is a very good way to deal with asymmetric saturation. We can also imagine to revisit the generalized sector condition by using better all the knowledge we have on all the different zones of the state space by adding several conditions like this. But it should be interesting also to consider asymmetry for other nonlinearity, in particular like backlash, quantization, and friction, because for the moment we consider that we have the symmetry of the nonlinearity. Oops. Another very interesting direction is the fact to be able to preserve the direction of the control. It is, for example, the case in some power systems or tire force systems. And in this case, we have to deal with non-decentralized saturations. Okay. So in a certain sense, we revisit the saturation because the saturation will be defined differently from a norm. And we can describe the saturation in a certain sense, like a certain nonlinearity beta of u to be defined, multiplying u. Okay. As mentioned at the beginning of this talk, we can revisit other problem like the study of the convergence of optimization algorithm. We can also expand the study to more complex classes of system like PDE systems, at least for some class of PDE. Another interesting point, because we have had some saturation of dead zone with variable threshold in order to improve the performance of the system, we can deal with time varying saturation levels directly, because this kind of problem appears in some control in the satellite. It's not so obvious to deal with this in order to have not so conservative conditions, and to consider dynamical nonlinearities. And all the elements I presented during this talk concern the nonlinearity in the input. And if we consider the nonlinearities in the output, the things are more complex. And if we try just to revisit the condition and deal with this, for example, for the backlash, it's very conservative. So we need to revisit this in order to deal to revisit the tools in order to be able to deal with this kind of nonlinearity. Thanks for your attention. It's then coming.